Okay, this is a great static equilibrium problem. Pause the video and read the question. Make sure you understand it. Okay, hopefully you've done that. So here's our setup. We've got the ladder leaning against the wall. The length of the ladder is 5 meters and it's 3 meters away from the wall. Just Pythagorean triplet gives us this other side is 4 meters. So this angle up here is 36.9 degrees, which means this angle in here will be about 53 degrees. We'll use that in a minute. So all the forces on our ladder, its weight we put right in the center at the center of mass. So that's the weight of the ladder. We get the weight of the man. We're going to assume for a moment that he's not past the middle. We've got a normal force pointing up and a frictional force keeping us from sliding. The bottom of the ladder wants to slide away. This frictional force stops it from doing that. And we've got a normal force up here against the wall. The problem told us there's no frictional force against the wall. Okay, we're in static equilibrium, which means the sum of our forces must be 0. So the forces in the x direction are this normal force against the wall and this frictional force. So those must be equal and opposite. That's going to come in handy. This frictional force is the same in magnitude as this normal force against the wall. Then the y forces must all add up to 0. So this normal force here is holding up the weight of the guy and the weight of the ladder. And keep in mind, our frictional force is always less than or equal to mu times this normal force. Question A asks for the maximum frictional force, so that's when those two will be equal. Okay, so just from equation 2 here, we know both of these weights. We get this frictional force on the floor must be 900 newtons. So this maximum frictional force, this normal force here, must be 900 newtons. So the maximum frictional force is mu times n, 360 newtons. Part B says, now the guy's standing 1 meter up the ladder. We want to find out not what the maximum friction is. We haven't reached that yet. We don't want the ladder to fall, just how much friction we have. We can put our axis of rotation anywhere we want. It's always convenient to put it someplace that's going to cancel out some of our torques. So I have the most forces down here at the bottom. I decided to put the axis right here at the bottom, so these two torques will be 0. They're distance 0 from our axis. Then each force will create a torque, magnitude of the force times the distance from the axis times the sine of the angle that force makes with the ladder, which is our line of action here. So the guy here is creating a clockwise torque. He wants to make the ladder rotate clockwise, so he's a negative torque. His torque will be his force. His distance is 1 meter from the axis times the sine of this angle in here, which we found was 36.9 degrees. The weight of the ladder itself is the torque from that is its weight times its distance, half the length of the ladder, 2.5 meters, times sine of the angle. This guy up here, his angle is 53 degrees because he points horizontally. So his torque is also positive, by the way. He tries to make us rotate counterclockwise. His torque is the magnitude of that normal force times his distance, 5, times sine of 53. So the sum of those torques must be 0. Just a little algebra gets this normal force up here against the wall is 171 newtons. But we decided just a minute ago that and the frictional force must be the same. These two must be equal and opposite. So then our frictional force is 171 newtons. Okay, then in part C, we want to know how far up the guy can go before the ladder slides. So at first when I was going to do this problem, I was going to put the axis of rotation here right in the center. And honestly, it wouldn't be a bad problem. We could do that. But I thought it might be easier if we put the axis still down here, so these two are 0. We find our sum of the forces so that this normal force is that maximum frictional force. Remember, these two have to be equal. So if this guy maxes out, the ladder will start to slide, but these two are equal. So I'm going to set this force equal to that maximum we found a minute ago at 360. Solve some of our torques must be 0 and see what this distance must be. So we're still rotating around right here at the end of the ladder. So we find each guy's torque. Now our distance for the center of mass is still 2.5. The distance for the guy is d. That's what we're looking for. We add up all three of our torques. Notice for the guy I've got a d in here. Notice for n, I've plugged in the maximum frictional force, 360. We solve and we get 2.7 meters. So he's past the center of mass. He's more than halfway up the ladder. If he goes any further, the frictional force here will overcome the maximum frictional force and will start to slide.